Hello. It took a few weeks for anyone to ask, but I'd been kind of waiting to see if people were comfortable with this particular standard. And judging by the standard quizzes people have turned in, it looks like people are. Having said that, though, I've had a couple of people ask this week if they could sort of see an example or sort of explanation of where it comes from. So I'm making this video really fast while I wait for my food from DoorDash to arrive. As a heads up, I'm not feeling so great right now for some reason, but I'm just going to try to do this and pass the time. So to kick things off, just to kind of introduce which question we're talking about here, we're talking about question number 6 from the standard quiz. In Honors Pre-Cal, it's specifically the Honors Pre-Cal standard quiz. That's the one that involves this sort of factoring thing. And the instructions say to factor and simplify the expression completely. Now, in truth, the strategy that you're using here is just GCF factoring. Like, that's all it is. GCF factoring and then a little bit of the distributive property. But at the same time, it's something that either you might not have seen directly modeled in Math 3, or it might just be something that looks a little intimidating and you could use a quick little explanation for. So that's my goal here. Very quickly show you, of course, what's happening, what you're doing, and why it works, and then actually execute 2 examples of it, including this one, but I'll save that for just a little bit. So to kick things off, I pointed out that the strategy that we're using here when it says to factor is GCF factoring. And for instance, if you'll recall, if you were trying to factor the expression, let's say 20x minus 12, you'd be trying to figure out like what factor goes into each of those terms. So in other words, you might think about this as 4 times 5 times x minus 4 times 3, and you'd see that both terms have a factor of 4 in them. So you'd factor out a GCF of 4. That would leave you the quantity the quantity 5x minus 3. That's completely equivalent to 20x minus 12, but it's fully factored because we pulled out that GCF. Now over here on the left, I have an expression that doesn't quite look like what you're going to see on the standard quiz or what you have seen on the standard quiz, but it's really similar. It's got the same structure. There's 2 different factors in here. There's powers of x and powers of y in each of the 2 terms. Notice they're terms because they're being added. And they've got different powers here. X has 7 and 5, and y has 3 and 11. Now, if I asked you to factor and simplify this expression completely, we're not going to be able to turn it into something that's just gloriously simple and clean, but we are going to be able to pull out the GCF, meaning the greatest common factor, whatever pieces and factors both terms have. And in order to do this, it might take a little bit to think about, but the shortest way to think about this is you want to take out the smaller power. You want to take out the smaller powers of each factor. And again, I wouldn't write out these instructions, obviously, while I was doing the problem in context, but that's what's happening here. Because if we want the largest factor that both have in common, the largest one is actually going to be the smaller power, because you've got to be able to pull it out of both terms. So for instance, if I take this one, again, this isn't how I do the problem. I would just do this off the top of my head. I think I could do it right now if I wanted to. But if I wanted to pull out the smaller power, I'd identify that there's an x to the 5th in this term and a y to the 3rd in that term. Notice that y to the 3rd is smaller than y to the 11th, or has a smaller power, and that x to the 7th has a larger power than x to the 5th. So basically we're set up. So now to kind of emphasize this sort of structural idea of what's happening here, we could instead write this as x squared times x to the 5th times y to the 3rd, and then plus x to the 5th times y to the 3rd times y to the 8th. Now, if you want to check, you can check me and make sure that everything adds up. I'm pretty confident it does. But if you notice, what I'm doing here is I'm trying to basically recreate this situation. Can we now see everything that each term has in common? And the answer should be yes. I see an x to the 5th in both terms, and there's an x squared over here, but there's no more x's on the right side. So that means x to the 5th is the largest factor we can pull out of each one. So x to the 5th will be part of our GCF. Likewise, I see that we have y to the 3rd on the left and on the right, and while on the right we have y to the 5th, or y to the 8th, we have no such other y pieces over here on the left. So that tells me y to the 3rd will be part of our GCF. So what do we do then? We pull out that GCF from each term. So I'll pull out an x to the 5th, I'll pull out a y to the 3rd. So in a sense, it's almost like we've just divided the expression by x to the 5th, y to the 3rd, but in a sense, we're just pulling it out. The same way we pulled the 4 from each of these, we're pulling the x to the 5th and y to the 3rd out. We're sort of anti-distributing, if you want to think about it that way. That's really what factoring is. What's left over then when we do that? Well, we pulled out x to the 5th and y to the 3rd. We're left with x squared from the first one, because notice there was nothing written in there. And we're left with y to the 8th from our second term. And there is our answer. That would be what the factored and simplified expression would be. Nothing more we could do. Now, if you're looking at this going, wait a second, did that work? you could just distribute the entire thing back in and see. So x to the 5th times x to the 2nd is x to the 7th, and we have y to the 3rd. On the next one, we have x to the 5th, and then y to the 3rd times y to the 8th is y to the 11th, and hey, look at that. It's the same thing we started with. We've just anti-distributed it. We've undone the distributive property to write it in the simplest possible form. So that's the idea behind what we're about to do in this standard quiz question. So we're going to pull out the smaller power for each factor. That is our strategy. So let's show you what that looks like. So I'll pop this up here. There's our sort of slogan or our motto of what we're going to do. But we're going to do the exact same thing. Now, we don't got just x's and y's anymore. We don't have x's and y's anymore. We've got x minus 8s and x plus 4s, but the same strategy is going to apply. So I'm going to use some colors here to help me see it. So I want to figure out what the smaller power of each factor is. So first I look at x minus 8. I see an x minus 8 on the left and on the right. The smaller power is going to be the 5th. So I'm going to pull out, as part of my GCF, x minus 8 to the 5th. So I'll go ahead and do that. X minus 8 to the 5th is coming out. Likewise, we have x plus 4 to the 5th and x plus 4 to the 4th. The smaller power is to the 4th. So part of my GCF will be x plus 4 to the 4th. So now I don't want to rewrite this line just like I did on the previous page where I actually fully decompose it that way, but if you need to on this one, you'd be welcome to. I'm just kind of speeding through that process a little bit. I'm kind of showing where those pieces will be coming out. Now here's the thing, we just factored out the GCF, but that's not the whole problem, obviously. There's going to be leftovers. There's always leftovers, unless you order a perfect size meal, in which case, good for you. Nice efficiency. But in this case, there's going to be leftovers. So let's think about this. If we pull out x minus 8 to the 5th power from the first term, so looking right over here, we're going to lose, well, all of it. All that's going to be left over, it's going to lose all of the x minus 8 to the 5ths. On the other side, x minus 8 to the 6th, we just pulled out 5 of those factors. So this will become x minus 8 to the 1st. And in fact, usually what you'll see me do is just kind of ignore that power. I'll just drop it. We've now got an x minus 8 left over, but no x minus 8s in the first term. So there's my first bit. The second one that I can do, I can look at the x plus 4s. So we're pulling out 4 of them, the smaller of the powers. So when we do, all 4 of these are going to go away. And that means 4 of the 5 will be gone from the first term. And what that does is, once again, it leaves us with a power of 1. Now, this reason this problem exists comes from something in calculus. It's preparing you for a particular type of factoring that just happens to be really useful overall at kind of reviewing a bunch of factoring skills. But I will point out that it will always be 1 if these problems are written correctly. And I've written all the problems, so they should be correct this way. So you'll always be left with the first power. And what that means is our leftover factor features 6 and x plus 4, because those were left over. We pulled out 5 of the x plus, we pulled out 4 of the x plus 4, so there's 1 left over. And on the other one, we pulled out 5 of the x minus 8, so there's 1 left over. The second term will be 5 times x minus 8. And so that's our leftover factor. Now this is good, this is great, but we're not finished yet. You can probably see why. This isn't as simple as we could possibly do it. Instead, I want to make sure that we finish this thing off. So I'm going to distribute each of those coefficients. So basically we're going to combine like terms, by the way. That's what we're doing. So I distribute the 6 in. I'll get 6x plus 6 times 4 is 24. Plus 5x minus 5 times 8 is 40. And if we take one more line here, just to kind of finish it off, and yes, I'm cheating, but I want the video over. This isn't as fun as I'd like to pretend it is. If we combine like terms here, we'll have 11x, and then plus 24 minus 40 is minus 16. And I'll go ahead and just clear that out. And right there would be our maximally factored equation. So again, what was our strategy here? We basically looked for the smaller power in each one because that would represent part of the GCF because it comes out of both terms since it's smaller. And then after we pulled out those pieces, we had some leftover pieces, which is a sum of 2 binomials. We distributed a little bit, and then we were able to turn our leftovers into kind of a nice little simple answer. And if you're wondering what you could do with this, it's a fairly narrow context in calculus, but this would actually help us identify where the maxima and minimas are. So where those high and low points are, we wouldn't need a calculator to do it like we did in pre-cal. So just kind of a nice little thing. So I've done one problem. Let me do one more just to hopefully nail it. And I'll go at a little bit more of a what's the word? I'll go at a little bit more of an aggressive pace if I can get my computer to cooperate. There it is. Okay. So the last one we're going to look at. And then I can render this video. So once again, we've got a product of binomial powers. That's the name of this, by the way, the product of binomial powers. We want to, actually this is the derivative of a product of binomial powers, but the word derivative doesn't mean anything to you just yet. So whatever. So in looking here, I once again want to identify the smaller power. So looking at the smaller power, I see 2x plus 1 to the 4th and 2x plus 1 to the 5th. The smaller power is 2x plus 1 to the 4th. Next, well, and let's think about that. If we pull out 2x plus 1 to the 4th, all of them go away, and 4 of them go away, leaving us just 1. There's our first factor. The second factor is 3x plus 7 to the 3rd and 3x plus 7 to the 2nd. The smaller power is 3x plus 7 to the 2nd. That means that both of these will come away, and 2 of the 3 will go away, leaving us just 1. That leaves us with 2 products to add together. We have 10 times quantity 3x plus 7, and then plus 9 times quantity 2x plus 1. Again, in these problems that you'll face here, there will always be linear. It'll always be a sum of linear factors. Last but not least, we're going to distribute. And I'm going to do this. This is kind of my way of saving a little bit of space. I mean, yeah, I could do this in my head, but to demo what I'm doing here, if I distribute, I don't want to really have to write the entire thing again, so I'm not going to. I'm just going to kind of distribute it out so I can see what this last factor is. There we go. And now when I go to write my final answer, oops, 3x plus 7 to the 2nd. My final answer will have in that factor 30x plus 18x is 48x. And then 70 plus 9 plus 79. And there is my final answer. That's the most factored version. Now, the only thing I'd say is in all of the examples I showed you, this factor we got from the leftovers, it never GCF'd out itself. But I mean, it is possible that that last factor, you could have some stuff and get something like 2x plus 10. If that happens, you would be expected to pull out a GCF of 2 and move it out to the front side. So again, I wasn't able to come up with an example that had that happen, but it is something that you could run into. Having said that, that completes what I'm doing here. Hopefully that was sufficient and it gave you some information. For those of you who didn't know how to do it and asked, I hope this was a good resource for you to add to your collection of resources. For those of you who have just been pretending like you know how to do it, I mean, I guess shame on you, but here you can actually learn how to do it now. So thanks for watching. Have a good night.